All right, let's dive into something that sounds like it's straight out of science fiction, but is actually the hidden engine of, well, pretty much our entire modern world. We're talking about complex numbers. And you're about to see how a simple, quote-unquote, imaginary idea completely unlocked a new reality for engineers, scientists, you name it. And this quote from the mathematician Jacques Hadamard, it just perfectly sets the stage. The shortest path between two truths in the real domain passes through the complex domain. Think about that. He's basically saying that to understand some real-world truths, you have to take a detour through this imaginary world. This isn't just some clever math trick. It's a fundamental path to understanding reality.
So that really brings us to the core question, doesn't it? What are complex numbers? And why on earth did we even need to invent them? Well, it all kicked off with a really simple question, a question our good old familiar numbers just couldn't answer.
Okay, so first things first, let's set up the problem. For centuries, the real number line felt complete. It was perfect. It could handle anything we threw at it. Counting stuff, measuring things, you name it. But turns out there was this tiny hidden crack in the foundation.
And this is it. This is the equation that broke math for a while. Seriously, just think about it for a second. One number times itself gives you a -1. Well, a positive times a positive is positive, and a negative times a negative is also positive. There was just no way to do it. On that nice, neat number line we all know and love, no solution. The system was broken. So what do you do when a tool you need just doesn't exist? Well, if you're a mathematician, you invent it. And this was a big one. They realized this wasn't about just finding some new number hiding on the line somewhere. No, this was about creating an entirely new dimension for numbers to live in.
And here it is, the hero of our story, the number I. The solution was just to define it into existence. We just say, okay, from now on, I is the square root of -1. That's it. By just accepting this one little imaginary number, a whole new universe of math opens up. And the key, the one thing you really got to remember, is that if I equals the square root of -1, then I squared times has to equal -1. That one rule is the key that unlocks everything.
So this brings us to what a complex number actually looks like. The standard form is a plus bi. Think of it as having two parts. You've got the real part, a, that's just a normal number. And then you have the imaginary part, b, which is basically telling you how many i's you've got. Simple as that.
Now, this is a really huge leap in thinking. Real numbers, they all live on a single line, right? But complex numbers have two parts, so a line just won't cut it. They need a plane, two dimensions. We call this the complex plane. The horizontal axis is for the real part, and the vertical axis is for the imaginary part. Suddenly, numbers don't just go left and right, they can go up, down, and everywhere in between.
All right, so we've got these new numbers living on a whole plane. You might be thinking, oh great, the math is going to be a nightmare. But here's the best part. The rules are actually super familiar and make a lot of sense.
Look, for adding and subtracting, it's easy. Just keep the real parts together and the imaginary parts together. If you've ever done basic algebra, like combining x's and y's, you already know how to do this. You just combine like terms.
Multiplication is pretty much the same deal. You just multiply them out like you would with binomials. The FOIL method. But there's that one crucial trick we talked about. Anytime you see an I² pop up, you swap it out for a -1. That's the whole game. It's the move that magically pulls an expression back into the real world. Okay, before we get to division, we need to introduce a special tool, kind of like a secret weapon. It's called the complex conjugate. All you do is take a complex number, say a plus bi, and you just flip the sign in the middle to get a minus bi. That's it. It seems like a tiny change, but trust me, it's a powerhouse. And here's the magic. When you multiply any complex number by its conjugate, something awesome happens. The imaginary I terms completely cancel each other out every single time, and what you're left with is always a purely real number. And that is the whole secret to handling division.
So how do you divide these things? I mean, the big problem is you're not really supposed to have an I in the denominator of a fraction. So what do? You use our secret weapon. You multiply the top and the bottom of the fraction by the conjugate of the denominator. The denominator magically becomes a real number and poof, problem solved. It's a really elegant trick.
Okay, so we've got the basic math down, but now let's switch gears a little. There's another way to look at these numbers, a much more geometric way. And this new perspective is what really unlocks their true power.
Right now, we've been thinking in rectangular terms, right? Go over this much and up this much.
But there's another way, polar form. Instead of over and up, you just say, how far is it from the center and at what angle? It's just two different ways of describing the exact same spot on the plane.
And these two new descriptors have their own names, of course. That distance from the center, r, we call that the modulus. It's basically the size or magnitude of the number. And the angle, theta, that's called the argument. Modulus and argument. That's all you need for the polar form.
And this is where things get really cool. This polar form isn't just a different way of looking at things. It's a superpower. Why? Because of something called de Moivre's theorem. It says that to raise a complex number to some power, you just raise the modulus to that power and multiply the angle by it. That's it. It is so much easier than multiplying it out the long way.
This amazing tool just elegantly solves problems that used to be a real headache, like finding all the roots of a number. Let me ask you, what are the cube roots of 1? I mean, 1 is obviously an answer, but are there others? It turns out there are 2 more. And using this theorem, you find that all 3 roots are perfectly symmetrically spaced around a circle, forming a perfect equilateral triangle. How beautiful is that?
So, we've gone through the what and the how, but now we get to the really big question, the why. Why should you care? Who uses this stuff outside of a math class? Well, this is the ultimate payoff. This is where the story comes full circle, and we see how these imaginary numbers build our very real world.
I mean, just look at this list. We're talking electrical engineering, signal and image processing, quantum mechanics, fluid dynamics. These aren't just abstract ideas. These are the foundations of our modern lives, and every single one of them depends on complex numbers. That little imaginary number, I, is absolutely essential for describing reality.
Here's a fantastic way to picture it, especially for electrical engineering. You know how AC voltage goes up and down in a wave? Well, you can think of that wave as just the shadow or the side view of something that's actually rotating in a perfect circle on the complex plane. What we see as oscillating is just the real part of that rotation. And that's the genius of it. Engineers can use a single complex number, they call it a phasor, to pack in 2 crucial bits of info at once. Its magnitude, or modulus, tells them the voltage, and its angle, or argument, tells them its phase. One number does the job of 2, making the math for incredibly complex circuits, well, way more simple.
So think about where we started, with a problem that seemed literally impossible to solve, the square root of a negative number. And we ended up with a tool that's absolutely essential for building the world around us. It really makes you wonder, right? What other ideas out there that seem crazy or impossible today are quietly laying the groundwork for the reality of tomorrow?